Okay, so now I've done a little bit of preamble, let's actually try the problem. So let's start off with, it's an indeterminate problem, isn't it? So we've got this attached to the wall here. So I'm going to have a reaction RBX, RBY. Since this is attached to the wall, we're going to have a bending moment at the wall. I'll call that MB. And then on the other side here, I've just got a pivot on rollers, so that leads to RAY. Throughout we've got distributed load, which can be written as W equals W0 X over L, where that is going to be peaking at W0, and we've got a length of L. Right, so what else? That's about it. So let's apply forces and whatnot on our external forces. So sum up forces in the x direction. So that then gives me RBX equals 0. No big deal. Now sum up the forces in the y direction. What we got there? We got RAY plus RBY, and now how do I deal with that load? Right, so I use my preamble here. So the weight of that load is going to be the total weight, so that's going to be WL, so little WO L squared over 2L, so that's little WO L over 2. So take away little W O L over 2 equals 0. I'll leave my equation like that. So it's my first equation of use. And then the next one is we'll take moments. A is the obvious location. Take moments at A. Well, I've got a clockwise MB. And then we've got, this is going to create a turning moment, RBY, RBX just goes to the middle, it's 0 anyway, so that is minus RBY times L equals 0. No, I've forgotten my distributed load again, haven't I? So it doesn't equal 0. So now let's look at the distributed load. So that is, again, remember our preamble. The centroid of the weight is 2/3 x away from, or rather that'd be 2/3 L away from the base. So we've got distributed load acting there. This is going to be a positive. Its weight is that WOL over 2 multiplied by this distance from here to here, which is 2/3 L equals 0. That's my second equation. Tidy it up, I suppose, before I move on. MB, take away RBY plus WO 2's will be cancelling. L squared over a third equals 0. Okay, so that will be my second equation there. I'll use that one. Right, so I've done that. What else can I do? The next thing I can do is to take a cut through my beam and then look left of me. So I'm going to take a cut there, look left, then that's going to expose internal forces. A V and an internal bending moment. It's only the internal bending moment I'm interested in. Right, so we're here, and let's look left of us. Can I go straight to M? Probably yes. So M is going to equal this thing here from there to there, so this will be an arbitrary distance x where I've made my cut, and I'm going to go clockwise, so that would be positive, so RAY times x, and this weight, which will be 2/3 from here, so this total distance will be 2/3 to get to there, so that's a minus. I will need to use my result, so we're left of that x, so that's our weight, so little WO x squared 2L, and where's our position? So we want the distance from here to here, okay, and so that is obviously going to be a third x, if this is 2/3 to get to there, so that's 1/3 x. Tidy this up, RAY x, take away W0 x to the power 3 6L. So I've got an equation for M. Next thing is we're going to stick that in and integrate it twice. So EI, I've taken that over to the left hand side. Second order differential, and we're going to put that in, put the M here, so RAY times x, take away W0 x to the power 3 6L, so that's my right hand side that needs integrating. Right, so integrate once, EI delta y over delta x, that's the left hand side integrated, integrate the right hand side, RAY x squared divided by 2. Now let's integrate this, W0 x to the power 4, 4 times 6 is okay, hopefully. Right, so we've got 6 times 4, so that's going to be 24L. So that's my first one there. So shall I start applying boundary conditions? Plus C1. I think I might as well. So boundary conditions I could apply. The only boundary condition I can see here for this problem is I can imagine, let's go to another page, this problem would be such that, because this is fixed to the wall, and then it's going to drop down here, and then it's going to be pushed back where that pivot is. So it's going to look something like that. So at the wall here, delta y over delta x equals 0. So I'll apply that boundary condition, so we're at L. So when we are x equals L, we're expecting this to equal 0. This equals RAY L squared over 2. Take away W0 L to the power 4 over 24L plus C1. That's not great, is it? C1 equals W0 L to the power 3 over 24. Take away RAY L squared over 2. Right, so let's carry on. Now let's integrate this again. So that's going to give me E1 y, which is going to be a function of x. Integrate this. That's going to give me RAY x to the power 3 over 6. Now integrate that. I'm getting big numbers now. X to the power 5. I think I could do that in my head, but my head needs sleep. 24 times 5 is 120. I'll keep calling C1 just C1 for the moment. X plus C2. Right, so now I've got this. What other boundary conditions can I apply? Obviously I've got y equals 0, x equals 0. So this one here. And I've got y equals 0, x equals L. That one there. So this one is a nice one. We can apply, so we've applied this boundary condition. This will be the second one to apply. So that gives me E I y when x equals 0, y equals 0. Okay, that's 0, that's 0, that's 0, C2 is 0. Okay. What do I want to do next? Go back and substitute and start finding the reactions, I suppose. Yeah, the only thing I've got left really I can think of is to apply the boundary condition 3, this one up here, and then go back and substitute my original equations. So we've got E I y when x equals L. That's RAY L to the power 3 over 6. Take away little w L to the power 4 over 120 L plus C1, which is little w L to the power 4 over 24. Take away RAY L squared over 2 times by L. Let's tidy this up, and this equals 0. So tidy this up, we get RAY times L to the power 3 over 6, and here I've got to take away RAY over 2 L to the power 3. Okay, this I'll move over to the right hand side, so I've got W0 L to the power 3 over 120. What have I gone wrong there? So I miswrote that, so oh no, I didn't. What have I gone wrong there? C1 that's wrong there, so that should be to the power 3. Still not correct. Okay, too early in the morning, that should be to the power 5. Just writing things down incorrectly. So L to the power 3 and then L to the power 5. So that leaves me with L to the power 4. Boob. So take it over to the right hand side, minus W0 L to the power 4 over 24. Right, can't be bothered, let's use my calculator. 1/6 take away a half, that's a third. So we got minus 1/3 RAY L to the power 3 equals 1/20th. Take away 1/24th is minus 1/30th. Minus 1/30th W0 L to the power 4. So the L's are going to cancel a lot. So we've got multiply both sides by minus 30. So that gives me 10 RAY, divide through by L to the power 3, minus 30 W0 L. So and I'm getting the wrong answer. Or am I? Okay, I had to go and have breakfast. Let's come back. Where are we? So we've found RAY equals 1/10 of W0L. So remember that is going to be, the total weight is W0L over 2, so it's a fifth. So it sounds kind of like the right answer. I wonder if it is the right answer. Can't see. Yeah, that's correct. Right, so now let's go back and find where we can find RBY. So we can use this one here. So RAY plus RBY equals W0L over 2. Therefore RBY equals W0L over 2 take away 1/10 of it. So 5/5, no sorry, 5/10 take away 1/10, leaves me with 4/10, so that's 2/5. Was I required to find RB? Derive the equation to determine the slope at A. Determine the reaction at A. Okay, well I wasn't supposed to find that one. Never mind. So I found the reaction, and it sounds right. Next is state what the equation is. So that's going to be a mess. So we've now found RAY, C1, so we can go back to this equation and write it all out. Right, so we've got EI, Y, a function of X. RAY is 1/10 of that. W0L, so that becomes 60 x to the power 3 minus W0 x to the power 5 1/20th divided by L plus C1. Now C1 is W0 L to the power 3 over 24. Can we see it? Let's bring it into shot. Okay, you can't see me doing this stuff here. Okay, that's that. So we're now doing C1 there. Take away RAY L squared over 2 times by X, and C2 I'm fairly sure was 0, wasn't it? C2 was 0. Right, so that's the equation for our y. So notice we've got interesting bring that term in front. x to the power 5, x to the power 3, x to the power 1. Is anything simplifying here? Oh, I've got a substitute in there as well, sorry. So we've got W0, let's write them in order of powers. So I will take W0 over L to be my common factor. So that gives me minus 120th x to the power 5. Now this one here, plus, so we've taken out WO over L, so I need to put another L in here, so that's going to give me L squared x to the power 3 divided by 60. Now this one here, I want to substitute in RAY is W0L a tenth. So that would be 1/24 divided by 1/24, take away 1/20. So that's a minus 120. So it's a minus it's a negative, isn't it? 120 W0 no, I've taken the W0 out. I've taken L out, so that becomes L to the 4 times by x. Looks like it would be a sensible thing to take out either minus 120th or 120th itself. So you could leave the answer like that. So we could maybe take that out. W0 120 L. So we have a leading term of minus x to the power 5. So that means I have, if I've taken out 120 here, so I've got two of them. Is that right? Yeah, I've got two of them. Plus 2 L squared x to the power 3. Notice your powers are always adding up to 5. And here minus L to the power 4 x. Again 4 plus to the power 1, so 5 again. So that's my equation. I could maybe do a plot of this to see how that looks like. Okay. But we're still not done, because we found the reaction, we've done that equation, deformation, and we've determined the slope at A. So what I'm expecting is a negative slope here. What do I get? Right. go back. Find my differential, so that's this one here. So EI delta y over delta x equals RAY x squared over 2. Take away W0 x to the power 4 24 over L plus C1, which is W0 L to the power 3 over 24. Take away RAY L squared over 2. Okay, so that's that equation there. RAY is W0 L over 10. So we need to substitute that into here. So EI, strictly speaking, that should be on the bottom, on the other side. Never mind, leave it there. So RAY is W0L, so the first substitution is going to give me, I'm going to end up with a lot of W0s. Got an L there, so I'll take out that as a common factor. So we're going to end up with W0 over L. Right, substitute that into there. I've taken out the L, so that needs to become L squared. So everything's going to be to the power 4. L squared x squared. And then on the bottom, we've got 2 times 10, so that would be 20. Okay, next one, take away, taking out the W, taking out the L, so it's just going to be x to the power 4 over 24. Fair enough. Next one, plus, taking out the WO, that needs to become L to the power 4 over 24. Right, take away this. Now substitute this in here, so we've got W0, so that's going to go out, and that becomes L to the power, I must have done something wrong here. Oh yeah, because I'm taking out L's there, so that will be so that, yes, that's where that's coming from. So the L to the power 3 becomes L to the power 4. Here it's going to become L to the power 3 because of the L there. Then with this L here it becomes L to the power 4. So L to the power 4, and then we've got 2 times 10. So that's a 20. So same calc as before. 1/24, take away 1/20. So that'd be minus 1/20. So let's take out the 1/20. So 120 L squared x 120 divided by 26 120 divided by 24, 5. And that was minus L to the 4. Yeah, because that was a minus 1/20. So that's my equation for the gradient throughout the entire beam, but I'm only being asked to find it at position A. So that's when x equals 0. So that would be 1 over e We've got 120 there, and an L, and W0. Substituting x equals 0, x equals 0, it leaves us with minus 4L to the power of 4. So that's my answer. Minus W0, L to the power of 4 over 120 EIL. Obviously we should simplify that. Minus W0, L to the power of 3 over 120 EI. And that's correct. So the other way of saying that is that we know it's a gradient and it's pointing downwards by that amount. How long? 1 hour to do that problem.